The planet's dying and my laptop battery is running out, so let's make this quick. We are going to train our own deep learning model end-to-end in 5 minutes for the critical task of telling us, does this image contain a dog or not? This Doggy detector is a binary image classifier. Classification because we're putting each image into a category, and binary because there are only 2 possible categories, dog or not dog. A link to all the code for this with detailed explanations is in the description below, so you can run it yourself and pass it off as your own. 300 seconds on the clock. Let's f***ing go! There are 4 steps we'll need to do. Number 1, get some images to train on. Number 2, prepare these images for our model. Number 3, create our model. And number 4, see if it actually works. We're using a library called FastAI for this. It's a good starting point because it uses sensible defaults for a lot of the inner workings, so you can focus on high-level stuff for now. Step 1. We have some images from my personal collection. We'll just use 69 photos to show that you don't need anything too crazy to train a decent model. In this folder, we've got 69 dogs. In this folder, we've got 69 things that aren't dogs. We've got some cats, trees, Uncle Jagdish's holiday photos. These are all in a GitHub repository that I've linked to. We just want to download them so that they appear in our local storage here. This part isn't actually that interesting or relevant to machine learning, so I'll rattle through it double time. This creates the folders locally, and then these are the URLs we want to download them from, and this just loops through each file one by one to download it and save it locally. Step 1, done. Step 2, we create a data loader which structures our input into a standard format so that models can understand it. Believe it or not, this is where most of the legwork is. We define our inputs as an image input and our output as categories. We tell it that to get the training data, you need to use this function, which will take a file path to a folder, then recursively get all of the images in that folder. The labels for each image are the name of the folder. If the image is in the dog folder, the label is dog. If the image is in the not dog folder, the label is not dog. We can transform our inputs so that they are all in a standard format. Here, we're squishing them all to be the same resolution, 192 by 192 squares. We hold out some of our training data as a validation set. This validation set won't affect the model's training, but we use it as a sanity check to say, the weights you're learning from the training data should generalize to things it hasn't seen, so we should get accurate predictions on this validation set of unseen images too. We can then load batches of our data pointing at our training folder. Here's an example. Step 2, done. Now, we'll define which model we want to use. Here I'm going to use a pre-trained model called ResNet. Basically, some other poor sucker has already incurred the expense of training a big model. I just chop the end off and fine-tune a bit for my task. A model is just a mathematical function with lots of parameters. Think of it like a box with a bunch of knobs on it. Nope, not that. Yeah, that one. We can see what happens when we pass it an image. The input is a 3-dimensional tensor. This just means it's 192 by 192 pixels, and there are 3 channels for red, green, and blue. The output is 2 values, the probability that it's a dog and the probability that it isn't. We want to learn some complicated function that maps from these inputs to these outputs. To start with, it isn't great because we haven't trained it yet. If we move the knobs, the model's predictions will change. We know that this one is a dog, so if the model was perfect, it would output 1, 0. So now we can define a crappiness score. How far away is the model's predicted value from its target value? We can do this for every image in our training set, and then we can average that over all of the images in our training set. And this average crappiness score is really interesting. We have a single number that tells us how bad our model is. It doesn't matter how many dimensions our inputs or outputs have, or even what kind of data it is. We can always boil it down to one number. And because machine learning researchers are grown-ups, unlike me, they call this average crappiness score a loss. And the logic to calculate that score, in this case just taking the difference, is called a loss function. Now that we have this number that tells us how bad our model is, training the model is just a game of hot or cold to make that loss smaller. We turn the knob for our first parameter up a bit and see if the loss goes down. If it does, great, move on to the next one. If not, oops, try turning it the other way. Now just do that for all of the knobs. And this process of twiddling knobs is what the grown-ups call optimization. And that's all there is to training a model. A forward pass calculates the loss, and a backward pass twiddles the knobs. That's called one epoch. We're going to repeat that multiple times. On each epoch, we show the model all of our training data and nudge the knobs a little bit in the right direction. As long as you have some data and a loss function, all you need to do is play with your knob and you can achieve great things. If you remember just one thing from this video, let it be that. Here we're training for 5 epochs. And that's it. Our model is trained. Step 3, done. Now let's see how our model performs when it sees a new image. Here's a doggy that it hasn't seen before. This is my special little boy, Billy. It was his 7th birthday this week. If you want, you can leave him a birthday wish in the comments, and I'll make sure he gets them. Or if not, you can just live with the fact that you've disappointed him. I don't care, no skin off my nose. And look at that, gee willikers, it got it right. And now an image of something that isn't a dog. Oh, Jiminy Jillikers, it got that right too. Once more for good luck. Here's Billy again. Oh, now we're just showing off. Right, that's it. Step 4 done. Stop the clock! And that's all there is to it. Now you can go impress your Uncle Jagdish with your newfound computer vision deep learning skills. How interesting.